Hi guys, Dr. J here, and in this video we're going to be talking about GNSS, Global Navigation Satellite Systems. You probably have heard the more common phrase GPS, or Global Positioning Systems. We'll talk about the difference between these two in this lecture, and let's get started. So GPS is all around us. We have GPS receivers in our phones, in our watches, in our cameras, and I fly drones. We have GPS in drones. GPS is also used for surveying. It's used in tectonic applications for very precise measurements of location. It's used in surveying and civil engineering applications to locate all sorts of things. So GPS is really, truly all around us, and both on the ground and in space. So GPS satellites, are orbiting the Earth. The US system is called GPS, Global Positioning System. And there are multiple of these systems that belong to different countries. And we call the whole collective of all the different systems GNSS, or Global Navigation Satellite Systems. GPS is the US constellation, as I said, but Russia has a system called GLONASS. China has Baidu. Europe has the Galileo system, and India and Japan have their own regional systems. Now you might think, why would all these areas each have their own system? Well, it's partly a matter of national security. So China, Russia, the US aren't always on the best of terms. And so they want to each have their own system that they can use for themselves. But the other reason is that you might be more interested in certain parts of the world than in other parts. So for example, there's not that many people in Antarctica. There's a few scientists, but otherwise not that many folks are there. So you may want to optimize your satellite system to cover certain parts of the world more than others. And in fact, the systems that are in use by India and Japan are just that. They're especially highly optimized systems, which mostly cover areas around India and Japan. So these are all existing GNSS systems. And I'll kind of go back and forth in the lecture and in this class talking about GNSS versus GPS. But just know GNSS is the general term. GPS is the US specific constellation of GNSS satellites. Now let's talk a little bit more specifically about the US system. The US has currently about a little bit more than 30 satellites. These satellites are in orbit around the Earth at about 20,000 kilometers altitude, a 12-hour orbital period. This is the whole idea behind GPS satellite tracking. So some of you may have seen GPS receivers, and you can sort of track the satellite locations. And so at any particular place on the Earth, you might see 3, 4, 5, 6, 7 of these GPS satellites in the sky. Now, if you look up in the sky, of course, you won't see them most of the time because they're small and far away, but they're up there. And you can use GPS software, essentially, to track these satellites. Now, the other really important component of a GPS system is the ground control system. And you can see an image here on the slide of the ground control system, or part of the ground control system for the US GPS satellite constellation. You can see that there are a number of stations around the world, and this is important in order to be able to constrain satellites wherever they are orbiting the Earth. And basically the idea here is that these satellites know where they are by reference to these ground control systems, which have precise, established, known locations. So at some point, probably some astronomical surveying is done to each one of these sites. So they are very precisely positioned on the Earth from an astronomical perspective. Then those positions are used to work out the positions of GPS satellites. Those GPS satellites then have known positions based on this ground control system. And then those satellites can be used to determine the location of a receiver on the ground. We'll talk about how that's done in a minute. But just as a summary, this ground control system is used for locating the satellites, which is a very important component of the system. And also the control segment. This is just kind of a schematic of how the entire GPS system works. The control segment maintains the health and status of this satellite constellation and uploads navigational data, uploads navigational data, and then records positions of those satellites through time. The space segment, the satellites themselves are receiving that information and sending information to the ground control. But then they're transmitting one-way signals, which are being picked up by GPS receivers. And here's where most of us are in the user segment. You receive those GPS signals to calculate a user's position. So as I mentioned, we have ground control, satellites, and then antennas and receivers on the ground for users. Now, GNSS satellites broadcasts, I should have broadcasts here. They broadcast the almanac and the ephemeris data in the signals that they transmit. These are orbital parameters for all the GPS satellites, and this is so that your GPS can track those satellites. And these don't have to be super precise. They're just for locating purposes for your GPS. But the ephemeris data are very precise orbital and clock corrections for each particular GPS satellite. And this is necessary for precise positioning. We'll talk about the details of positioning here in a second, but basically a receiver needs to know where all the satellites are and at what time they were in those locations in order to be able to work out where it is on the ground. So let's take a look at this a little bit more detail at this signal which gets transmitted from the satellites. So there's a transmitted signal, and this is a low power signal, and it's a sequence of just computer language, ones and zeros, kind of a signal. And the thing to note here is that the transmitted signal is a known code. So it's the signal that's being transmitted, called a CA code or a P code. It has a known sequence. And so that your GPS receiver knows what this sequence is. You have your GPS receiver, which has a code, and then you have your received signal, which is driven by the satellite clock. And there's going to be some offset. And that offset is going to be partly due to the distance that it took from the signal to get from the satellite to your receiver. So the satellites are orbiting and they're transmitting radar signals. Those are electromagnetic waves. They take some time to travel from the satellite down to your receiver. And that period of time, if you knew what that time was exactly, then you could work out the distance from the ground receiver to the satellite in orbit. It's just the speed of light. You can see it here. The pseudo range here is called the speed of light multiplied by the difference in time between the receiver based signal and the received signal from the satellite. So this might be a little confusing, but again, we're receiving a signal from the satellite. We know what that signal is, and we can kind of match up that signal to the signal that's on our GPS receiver, do a comparison of the clocks, and basically work out the time that it's been since that signal was sent from the satellite. And that gives us our what's called our pseudo range. And it's just the speed of light times that time. Now, this is called a pseudo range and not a range because there are other things in here. We'll talk about those in a minute. There's errors and uncertainties. Basically, the receiver clock could be wrong. And there's atmospheric effects and all sorts of other things we'll talk about in a minute. But the radio signal from the satellite tells the GNSS receiver the satellite clock time and provides the most recent corrections to the satellite's positions. So you know the position of the satellite, you know the time, and you know basically the relative time between when that signal was sent from the satellite and when it was picked up by your receiver. This is the fundamental information you're going to use to work out a position. And then the GPS unit, your receiver, compares multiple satellite times to the receiver time and determines the distance to each one of these satellites. So there's multiple satellites involved here. And just as you can imagine, if you have 3 satellites and you're trying to work out your position in 3D space, you'll be able to do that. In other words, if you know 3 locations, at least, and you know exactly how far away they are, then you can work out where you are, what your location is relative to each one of these. And the reason that this works is because there's going to be only one location where the distance to all these satellites intersects at a single point. So just imagine if you have 2 circles here, you can see that those 2 circles are intersecting at 2 points. If you were to add a 3rd circle, there would be essentially just one location where all 3 circles would intersect. Now, it's a little bit more complicated because, as I mentioned, we have clock errors. We don't actually know what the correct time is at our receiver. The satellites know time very accurately, But our receivers don't know. The handheld receiver, the cell phone, the watch, whatever you have in your hand doesn't know the correct time exactly. And we're talking about exactly within a few nanoseconds. So, and even, just a small amount, a microsecond or a millisecond off of the correct time is going to result in a big difference in distance to a satellite, right? Because the speed of light is so fast, just a millisecond of time is actually quite a long distance. So you could end up with a big error in your distance. So the your receiver needs to actually calculate what the error is in your clock, in your local clock. And so you need not just 3 satellites, but 4 satellites. And so that's what you see on this plot. 4 satellites are the minimum requirement that you need to be able to work out a position plus a time correction to your receiver. So now you have these 4 satellites. You know what the distance is to each one of those satellites from where you are to those satellites, and you can work out your location. You can see here there's going to be only one point where you're the correct distance away from all the satellites. And so that's going to be your location on Earth. And then because you know what the satellite locations are, I should say your receiver knows what the satellite locations are, it's able to back calculate what your location is from those. Pretty cool. In order to do this, of course, you have to have a coordinate system. We've talked about coordinate systems in other videos. And basically, the idea here is that you're using some kind of Cartesian coordinate system. There's something called an Earth-centered, Earth-fixed coordinate system. We've talked about other types of coordinate systems, but the one that's used by satellites is Earth-centered, Earth-fixed. So you have an XYZ coordinate, and you're just measuring the satellite locations in this XYZ coordinate system, and you're measuring your location on the Earth in that XYZ coordinate system. And then, of course, your receiver needs to convert that to your latitude and longitude and height on the surface of the Earth. So as I just mentioned, we're using this Earth-centered, Earth-fixed system, and the GPS signal is communicating the position and velocity of the satellites at a particular time in order for your receiver to calculate its position on the surface of the Earth. How many satellites are required to determine your position in 3D space? Well, we already said that. It's 4 satellites because you need to know you have 3 unknown quantities, X, Y, Z location, and then your time offset. So you actually need 4 satellites to be able to calculate the position of your GPS receiver. GPS or GNSS works the same way regardless of whether you're using a very high quality GNSS receiver for tectonic studies, for example, whether you're using a handheld GPS, whether it's a watch, whether it's a cell phone, it all works the exact same way. Now, there are other kinds of corrections and things that you can use depending on your receiver. If it's a dual frequency, we'll talk more about that in a second. But the general way that a GPS works is the same way across all platforms. By the way, so how far off is your position, do you think? If your clock is 0.000001 seconds slow, so you're what is that, 1 microsecond off of your clock? So this is why a clock receiver clock error, fixing that is so important. It's because if you're a microsecond off, you can be 300 meters off in your location. So just imagine, GPS today produces an accuracy of, less than 3 meters, let's say. And if you had these clock errors, even just a microsecond off the correct time, you would be 300 meters off in your location. And this is just because of the speed of light. The speed of light, 3 times 10 to the 8 meters per second, times a microsecond clock offset, you would be 300 meters off in your position. So really accurate clocks are really important for GPS positioning. That's why we have those clocks, redundant clocks even, on the GPS satellites. And this is why we have to calculate for a clock correction when we do the receiver location. What kind of sources of error or uncertainties are in GPS positioning? Well, one thing that you can have is satellite orbit problems. So if you don't know exactly what the satellite orbit is, you don't know exactly where the satellite is, and that can lead to an error in your location. If you have clock errors, so even though those satellite clocks are extremely accurate, they might be accurate to a nanosecond. Sometimes that may introduce a small uncertainty. Even if it's a nanosecond difference, that still could be a small error in your location. Atmospheric delays are a big one. The speed of light is affected by water, electron content, and as well as other things, pressure and temperature, in the atmosphere and the ionosphere. So both the lower atmosphere, called the troposphere, and the ionosphere can affect the propagation of radar waves through them. They cause them to slow down, basically. And this is a spatially variable thing. So you can't necessarily predict at any time and place what the delay is going to be from the ionosphere and the troposphere. So this is a noise source. It's a source of error. However, the biggest source of error is the ionosphere. And it turns out that this source of error is frequency dependent. What that means is that you can use two different radios with two slightly different frequencies and correct your GPS signal. So most GNSS today use two frequencies, or at least two frequencies, to basically do an automatic calculation for what the ionospheric signal is and remove it from the estimate of your location. And this can be a pretty big signal, on the order of meters. So it's a very big deal, very important to be able to correct that. And actually, that's probably the single biggest, with today's processing software, going from single band to dual band is the single biggest improvement that you can have in a GPS location. Obviously, tri-band, 3 bands would be even more accurate, or would be even more, would help reduce that error even more. Multipath is something that happens to GPS antennas. They pick up signals from multiple directions. So the satellite signal is sort of transmitting signal out in towards the ground, and some of that signal will hit the GPS antenna directly, but some of that signal may hit the ground and actually bounce up to the GPS antenna from underneath, or it may hit a building and be reflected off the building into the antenna. It may hit a car or a person or a plant, and be reflected into the antenna. And of course, if that happens, then that's a longer distance that signal traveled from the satellite. Obviously, that results in a longer time estimated since the signal left the satellite. And that results in an error in the distance from the GPS receiver to the satellite, because there's this extra distance that the signal has traveled that isn't accounted for in the algorithm. And so this is called multipath. The signal from the GPS satellite doesn't take a direct path to get to the receiver. And the way to correct this is to try to avoid having other things around your GNSS receivers. There's also certain types of receivers that try to kind of shield the antenna from those signals coming from below, for example. But the main way that people try to deal with this is just by having GPS antennas that don't have things around them. Now you say, well, what if I have a GPS signal on a car or a GPS signal on a building? Is that going to affect the accuracy of those measurements? And the answer is yes, it will. But you can get around that by observing for longer periods of time. Or maybe you don't need to have sub-centimeter accuracy in your GPS measurements. Maybe you're good enough. Maybe your measurements only need to be within a meter or something like that. So these errors can be a little bit sporadic and random. But in general, I would say they're not going to be much bigger than the ionospheric signals, usually. And then, of course, there's human error. So humans can set up, if you're doing a GPS survey, you can set up the antenna incorrectly. You can do other things like that. This is mostly when we get into the surveying aspect of GNSS. We'll talk about that as well here in a little bit. Just to say a little bit more about these clocks, each GPS satellite has 4 atomic clocks to be sure that one is always working. Each costs $100,000, and probably more nowadays, and is accurate to within 1/1000th of a second, so a nanosecond. So these are highly accurate clocks. And this brings up a good point about making measurements with GNSS. So if you really need to have highly accurate measurements with GNSS, what you can do is you can average in time. You can take measurements over a long period of time and average them, and this will actually tend to improve your estimate of the location. Because it turns out that clock errors or multipath errors, these tend to be a little bit random in time, depending on what they're coming from. Atmospheric errors tend to change in time. So you can average through time and come up with a better position than you can just by taking a measurement for 1 second. So if you need a really highly accurate measurement, let's say you're surveying in a benchmark at a building, a new construction site, then you can take, let's say, several hours of measurements and come up with a really, really precise measurement for that location. So for a typical GPS, handheld GPS, you take one measurement. Used to say kind of 10-meter horizontal accuracy. Nowadays, I think a lot of these can do a little bit better than that, maybe 3-meter horizontal accuracy. But if you can make measurements with a high quality GPS receiver for several hours, let's say 8 hours, you can get uncertainties which are down in the sub-centimeter range in the horizontal. And vertical is always a little bit worse for GNSS just because of the geometry. You don't have satellites above the ground and below the ground that would help you constrain your location a little bit better. They're all kind of up in the sky. So your vertical accuracy is always worse, but you can still get centimeter accuracy vertical with GPS by measuring for a long period of time. Now, something that's important to keep in mind with GNSS data is that it's referenced to an ellipsoid. So GNSS data is usually recorded and reported using geographic coordinates, WGS84. And this can include a geoid model for heights, but typically is going to be ellipsoidal heights. So in other words, if you're using GPS to get your elevations, keep in mind that it's most likely going to be referenced to the ellipsoid and not to the geoid. So in other words, if your GPS says 100 meters, it's not going to be 100 meters above sea level. It's going to be 100 meters above the surface of the ellipsoid. Now, in most places around the world, these two things are fairly close together. So usually it's not going to be that big of a deal. But just keep that in mind if you're doing very precise height measurements, for example, for flood monitoring or something like that, you're going to want to be very careful about what heights you're getting out of your GPS, because your GPS heights are going to most likely be ellipsoidal heights. Okay, so let's talk about different types of GNSS systems. Now we sort of have our recreational systems, our watches, our cell phones. Maybe you've used a recreational GPS in the past. These are kind of lower accuracy, but very common. So most folks will be familiar with these. If you have dual frequency receiver corrections, then you'll be down in the 0.5 meter, maybe 1 meter accuracy at worst. But if you want to get better than that, you kind of have to do some of the other things, like observe for a long period of time. One way to do that is to use a kinematic system. And this is a system where you use the location of a known benchmark, and you reference all your other locations to that known benchmark location. And by comparing the two locations, we have two GPS, one at the benchmark and one somewhere else, we can actually do a really good job improving the corrections for a GPS. And that's because the errors that are leading to our uncertainty in our position don't change a whole lot from place to place. In other words, if you go from one side of the world to the other, the atmosphere, the troposphere, the ionosphere will be quite a bit different. But if you're within a couple of miles of each other, two locations, those are going to be very similar tropospheric and ionospheric noise. So we'll talk about that in a minute. Then you have static geodetic campaign systems. These are where you're out there and you're measuring data with very high quality receivers for several hours in order to get the best possible measurements of a single location. And probably doing this more than one day. And there's a huge societal value to GNSS and GNSS-enabled research. Most people use it, of course, for location and navigation, and this is a huge application of GNSS. But GNSS-enabled science also provides early warning systems for hazards such as landslides, volcanoes, and faults. There are GNSS stations monitoring large faults, large volcanoes, landslides all over the world, and this saves lives, literally. GNSS is also used for very precise measurements of measuring water resources such as snowpack, aquifers, tracking objects. And without GNSS, we could not know where things are without directly measuring them, for example, with tape measures and things like that. In fact, doing surveying before the advent of GNSS was much more complicated and required whole teams of people with chains and complicated instruments and all sorts of things. So GNSS really has a huge societal value. Okay, so this is our kind of summary of GNSS and how it works. GNSS is this powerful tool that we have, has tons and tons of applications. It's used all over the world. It's based on measuring distances to 4+ satellites of known position in 3D space. Those satellite positions are known. They're being tracked by that ground control station network that we saw at the beginning. And by measuring our distance to at least 4 satellites, we can work out what our position is. The main difference between, let's say, a consumer-grade GNSS in your phone, in your watch, and a survey-grade GNSS is this dual frequency correction. So we're going from meters down to tens of centimeters accuracy. This is a very important step in order to get to high precision GNSS, is this dual frequency component. And if we do additional processing, we do additional time averaging, for example, we can get errors less than a millimeter per year if we're tracking tectonic motions, or we can get positions that are well under a centimeter, for example, using RTK GPS. And then these GNSS velocities are used for tectonic studies, where it's used to keep track of plate motions, how plates are moving around, what kind of deformation is happening, and can be used for all sorts of applications related to natural hazards. So overall, GNSS gives us this really amazing set of tools to look at where things are and how things are changing in space and time. So super useful tool to be aware of and to understand how it works. Lots of other resources are out there online for you to check out. Hopefully you found this lecture helpful, and I'll see you in the next video.